Hello and welcome back to the channel. Today we're looking into one of the most fascinating and challenging areas of computer science, distributed systems mastery. In any distributed system, coordinating actions across numerous independent nodes presents inherent complexities. This often leads to two critical and closely related problems: leader election and consensus. Leader election is the process by which a single, authoritative node, which we designate as the leader, is chosen from a group of participants. This leader is then responsible for coordinating specific actions, such as handling all write operations, ensuring data consistency, or managing a replicated log. The rationale behind having a single leader is primarily to simplify coordination within the system, avoiding potential conflicts that could arise if multiple nodes attempted to perform the same action simultaneously. It provides a clear, single point of truth for certain critical operations. However, this process is not without its difficulties. A significant challenge is the split-brain problem, which occurs if network issues cause two nodes to mistakenly believe they are both the leader, leading to disastrous inconsistencies. Robust leader election mechanisms must also efficiently and reliably handle the failure of an active leader, quickly electing a replacement. Consensus, in a more fundamental sense, is about ensuring that all nodes in a distributed system unequivocally agree on a single value or state, even in the presence of node failures, network delays, or message loss. This agreement is absolutely foundational for building reliable distributed databases, implementing fault-tolerant state machines, and managing replicated logs that underpin strong consistency guarantees. A well-known theoretical result, the FLP impossibility theorem, states that it's impossible to guarantee consensus in a purely asynchronous network if even one node can crash. Real-world systems overcome this by employing practical techniques like using timeouts to infer failures and relying on majority rule rather than requiring absolute certainty from every single node. Now, let's briefly touch upon two prominent consensus algorithms that address these challenges. Raft was specifically designed with understandability as its primary goal, making it generally easier to grasp and implement compared to its predecessors. In Raft, nodes take on one of three roles: leader, follower, or candidate. The leader manages all log replication, followers simply replicate entries from the leader, and candidates are nodes campaigning to become the new leader during an election. The leader orchestrates all changes by appending new entries to its replicated log, which followers then diligently copy. If the leader fails, followers initiate an election where they become candidates and vote for a new leader based on who has the most up-to-date log. Raft offers strong consistency and is widely preferred for its relative simplicity. In contrast, Paxos is a family of algorithms designed for solving the consensus problem in networks where processors can be unreliable. Its core roles are proposer, acceptor, and learner. Proposers attempt to get their proposed value accepted by a majority of acceptors. Once a majority accepts, learners can confidently adopt that value. Paxos is renowned for its high fault tolerance and ability to guarantee safety even in challenging network conditions. However, it is famously more difficult to understand, implement, and debug compared to Raft, which often leads practitioners to prefer Raft in real-world systems. In large-scale distributed systems, maintaining a consistent view of the cluster's health and membership across potentially thousands of nodes is a non-trivial task. This is precisely where gossip protocols and effective membership management become essential. A gossip protocol is a highly decentralized communication method where nodes periodically exchange information, not with all other nodes, but with only a small, random subset of their peers. You can visualize this much like spreading rumors in a social network. If a few people tell a few other random people a piece of information, that information eventually propagates throughout the entire network, even if it takes some time. This inherent randomness leads to eventual consistency. Information will ultimately propagate everywhere, but not instantly. Gossip protocols offer extremely high fault tolerance because there's no single point of control that can fail and bring down the communication. They are also remarkably scalable, as the communication overhead per node remains relatively constant regardless of the overall cluster size. These protocols are widely used for crucial tasks such as membership management, which involves tracking which nodes are currently active, failure detection, identifying unreachable nodes, data synchronization, disseminating updates efficiently, and generally propagating overall system state information across a large cluster. Membership management, then, is the core goal of maintaining an up-to-date and consistent view of which nodes are currently active, alive, and available within a distributed system. This information is vital for tasks like routing client requests, maintaining data replicas, and orchestrating various cluster operations. This task is complicated by constant node failures, network partitions where parts of the network become isolated, and transient network glitches. Gossip protocols are ideally suited for this. Nodes periodically gossip about their own status and share information about the status of other nodes they know about. Over time, this continuous, random exchange of information allows all nodes in the cluster to converge on a consistent view of the cluster membership, even if some nodes are temporarily unavailable or messages are lost. Building on this, failure detection is often implemented using heartbeats and timeouts. A node periodically sends a heartbeat message to its peers. If a node doesn't receive heartbeats from a particular peer for a defined period, it infers that the peer has failed and marks it as unavailable in its local membership list. Popular distributed systems like Apache Cassandra, a NoSQL database, extensively use gossip protocols for membership and failure detection. Similarly, HashiCorp-Surf, a library utilized in tools like Consul, provides robust gossip-based clustering capabilities. In distributed systems, especially those that prioritize high availability and involve data replication, quorum-based systems provide a powerful and flexible mechanism to manage data consistency effectively. A quorum refers to a minimum number of nodes that must actively participate and agree, either by acknowledging a successful write operation or by responding to a read request, for a distributed operation to be considered successful. The fundamental purpose of using quorums is to achieve a balanced trade-off between data integrity, consistency, and availability in the face of node failures or network partitions. By requiring agreement from a majority or a specific subset of nodes rather than all of them, you can ensure that you always have access to a consistent view of the data without sacrificing too much availability. A common way to define these quorum requirements is through the quorum protocol, N, W, R. N represents the total number of replicas or nodes storing copies of a particular piece of data. W, write quorum, is the minimum number of replicas that must successfully acknowledge a write operation before that write is considered complete and confirmed back to the client. R, read quorum, is the minimum number of replicas that must respond to a read operation for the read to be considered successful. The system will then compare the versions received from these R replicas and return the most recent consistent version. The relationship between these three values, N, W, R, directly determines the level of consistency your system provides. Strong consistency is typically achieved when the sum of your write quorum and read quorum is greater than the total number of replicas, W plus R greater than N. For example, if you have n equals 3 replicas and you set w equals 2 and r equals 2, then w plus r equals 4, which is greater than n equals 3. This overlap ensures that any read operation will always intersect with at least one node that holds the most recent write, thereby guaranteeing that you always retrieve the latest committed value. A more extreme example aiming for strong consistency might be n equals 3, w equals 3, r equals 1, where all 3 replicas must acknowledge a write, but a read from any single one is then guaranteed to be consistent. Eventual consistency is often achieved when w plus r less than or equal to n. In this scenario, writes might not be immediately visible to all subsequent reads across the system. However, the system guarantees that given enough time and no further updates to that data item, all replicas will eventually converge to the same consistent state. For instance, n equals 3, w equals 1, r equals 1 allows for very fast writes and reads, but it carries a higher potential for temporarily reading stale data. Quorum-based systems also play a direct role in high availability. By choosing lower quorum settings, such as w equals 1 and r equals 1, you can prioritize very fast operations and maximum availability even if many nodes are down, though this comes at the cost of immediate strong consistency guarantees. Prominent distributed databases like Apache Cassandra and Amazon DynamoDB extensively utilize quorum-based consistency models, offering users the flexibility to tune their W and R values based on their specific application's requirements for consistency versus availability. In distributed systems, where events occur on many different nodes, each operating with its own independent clock, determining the true order of events, especially those happening concurrently, becomes a significant challenge. This is precisely where vector clocks come into play to establish causal ordering. The fundamental challenge arises because traditional timestamps alone are insufficient to define a global, unambiguous order of events. Clocks can drift, and a timestamp from one machine might not accurately reflect its temporal relationship to an event on another machine. A vector clock is a logical clock mechanism designed to overcome this. It's represented as a list or array of node_ID, counter, pairs, with one entry for each node that is part of the entire distributed system. The primary purpose of a vector clock is to establish a partial ordering of events, often referred to as a causal order, across these distributed nodes. This allows us to unambiguously determine if one event happened before another, happened after it, or if they occurred concurrently, meaning neither event causally affected the other. The mechanism works as follows. First, each node in the system maintains its own vector clock, initially set to all zeros. Second, whenever an event occurs locally on a node, that node increments only its own counter within its vector clock. Third, when a node sends a message to another node, it includes its current vector clock within that message. Finally, when a node receives a message, it performs a merge operation. It updates its own vector clock by taking the maximum value for each entry in its clock and the received message's clock. After this merge, it then increments its own counter for itself before processing the message. The concept of causal ordering is central here. If event A can directly or indirectly influence event B, for instance, event A sends a message that subsequently triggers event B, then we can definitively say that A must happen before B in the causal order. Vector clocks are meticulously designed to reliably identify this happened before relationship. Events that are not causally related to each other, meaning neither happened before the other, are considered concurrent events. Vector clocks are particularly powerful because they allow us to precisely detect these concurrent updates, which are often the underlying source of conflicts in eventually consistent systems. A practical limitation of vector clocks, however, is that their size grows proportionally with the number of nodes in the system. In very large clusters, this can make them somewhat unwieldy. Despite this, vector clocks are primarily used for critical tasks such as detecting conflicts in eventually consistent systems, where concurrent updates need to be identified and resolved, and for ensuring the proper ordering of operations in distributed databases to maintain logical consistency without relying on a perfectly synchronized global clock. In the realm of highly available and large-scale distributed systems, eventual consistency stands out as a widely adopted and prevalent consistency model. At its core, eventual consistency states that if no new updates are made to a specific data item, eventually all reads of that item across the distributed system will return the last updated value. It's a promise that the data will converge and become uniform throughout the system, but this convergence is not instantaneous. This consistency model is a direct practical consequence of the CAP theorem. Systems that choose eventual consistency prioritize availability and partition tolerance over immediate strong consistency. This means they are designed to remain operational and accessible even during network partitions, accepting that different nodes might temporarily hold slightly different, or stale, versions of the same data. The key characteristic of eventual consistency is that updates propagate asynchronously throughout the system. This implies that immediately after a write operation is confirmed, a subsequent read operation performed on a different replica might temporarily return an older version of the data. However, over time, as updates propagate across the network, all replicas will eventually become consistent and reflect the latest changes. Eventual consistency is widely adopted in real-world architectures for scenarios where immediate consistency isn't strictly required, and where high availability and massive scale are paramount. For instance, in DNS, updates to DNS records, such as changing a website's IP address, propagate globally over time. It can take minutes or even hours for all DNS resolvers worldwide to reflect the change, which is a classic example of eventual consistency in action. In e-commerce shopping carts, while critical during the final checkout process, the state of a shopping cart might not need to be instantly consistent across all user sessions globally. Minor delays in syncing updates might be acceptable for interim views. Similarly, in social media feeds, if you like a post or comment on it, that update might not appear instantly on every single follower's feed worldwide. It will eventually propagate to all users. Many popular large-scale NoSQL databases, such as Apache Cassandra and Amazon DynamoDB, offer eventual consistency as their default or as a configurable option, allowing them to achieve massive scale and fault tolerance where traditional strong consistency models would introduce prohibitive latency or complexity. Despite its benefits, eventual consistency introduces certain challenges that developers must actively manage. One common issue is read-your-writes consistency, where a user might perform an update but then immediately attempt to read that update from a different replica and temporarily see an older version of the data. Another challenge relates to monotonic reads, which guarantee that if a user performs multiple reads of the same data item, they will never see a rollback, where a subsequent read returns an older version of the data than a previous read. Eventual consistency doesn't inherently guarantee this without additional mechanisms. Finally, conflict resolution becomes critical. As updates propagate asynchronously, concurrent writes to the same data on different replicas can lead to conflicts. Effective mechanisms are needed to detect and resolve these conflicting updates to prevent data loss or corruption, which we will discuss next. In distributed database systems, particularly those that are eventually consistent or support multi-master writes, a significant challenge arises when simultaneous updates to the same piece of data occur on different replicas. This leads to data conflicts, and developing robust conflict resolution strategies is crucial for maintaining data integrity. Imagine two users independently editing the same document on different replicas. Both changes are valid locally. When these concurrent changes propagate, the system must decide which version to keep or how to combine them to achieve a single, consistent state. Various approaches are employed. Last write wins, LWW, which simply takes the update with the latest timestamp. Though this risks data loss if clocks aren't perfectly synchronized, application-specific logic, where custom code merges conflicting versions based on business rules, e.g., merging shopping cart items, version vectors/vector clocks used to track causality and identify concurrent updates, merge by value for combining elements in lists or sets, or even user intervention where conflicts are presented for manual resolution. Robust conflict resolution is crucial for maintaining data integrity in highly available, eventually consistent distributed systems. To store and manage truly vast amounts of data reliably across large clusters of network machines, distributed file systems are essential. We'll explore concepts from two pioneering systems, Google File System, GFS, and Hadoop Distributed File System, HDFS. These systems abstract away physical distribution, providing a unified view of data while ensuring fault tolerance and high throughput for massive datasets. Google File System, GFS, uses a master-slave architecture. A single master node manages all metadata, while chunk servers store the actual data in large, replicated chunks, example, 64 megabytes or 128 megabytes. GFS prioritizes large, sequential writes. Hadoop Distributed File System, HDFS, inspired by GFS, also uses a name node, master, and data nodes, chunk servers. HDFS is designed for batch processing of very large datasets with high throughput. Data is replicated for fault tolerance, and it emphasizes data locality moving computation to the data to minimize network transfers. Both GFS and HDFS excel in scalability, fault tolerance, data locality, and high throughput for large files. In distributed messaging systems, where messages flow asynchronously, ensuring they are delivered and processed in a specific order can be critical. This leads to different message ordering guarantees, where the level of ordering required varies by use case. The main types include no order guarantee, simplest and highest throughput. Messages arrive arbitrarily. Producer order. Per partition ordering guarantees messages sent by a single producer to a single partition are delivered in order. Common in Kafka for event streaming. Total order. Global ordering most strict and challenging. All messages in the system are delivered in the exact same global sequence. Requires complex mechanisms, leading to lower throughput. Causal order. If one message influences another, the influencer is delivered first, often tracked with vector clocks. Stronger ordering guarantees generally come at the cost of lower throughput, higher latency, and increased complexity. Understanding these trade-offs is vital for designing efficient messaging systems. One of the most fundamental and unavoidable challenges in distributed systems, famously encapsulated by the CAP theorem, is partition tolerance. Partition tolerance refers to a distributed system's ability to continue operating despite network partitions, communication failures that split the system into isolated segments. The CAP theorem states that in the presence of a network partition, P, a distributed system can only choose to prioritize either consistency, C, all nodes see the same data at the same time, or availability, A. Every request receives a response, but not both simultaneously. You must choose one during a partition. Systems are designed to behave in two primary ways during a partition. CP, consistency, and partition tolerance. These systems prioritize strong consistency. If a partition occurs and consistency cannot be guaranteed, the system will become unavailable for operations until the partition heals. Examples include Raft and Zookeeper, prioritizing correctness. AP, availability and partition tolerance. These systems prioritize availability. If a partition occurs, the system remains available on both sides, but this can lead to temporary inconsistencies that must be resolved later. Examples include DynamoDB and Cassandra, which favor high availability. Quorum-based systems allow tuning this balance. For AP systems, conflict resolution and anti-entropy mechanisms are essential to merge divergent states after a partition. The key is acknowledging that partitions will happen and designing explicitly for how your system behaves during them, based on your application's critical needs. To summarize our journey through distributed systems mastery, we've covered the essential concepts foundational for building robust and scalable architectures. We explored coordination through leader election and consensus. For discovery and health, we learned about gossip protocols and membership management. Our discussion on consistency covered quorum-based systems, vector clocks, eventual consistency, and conflict resolution strategies. We delved into distributed file systems for large-scale storage and examined message ordering guarantees for reliable communication. Finally, we reinforced resilience through understanding partition tolerance from the CAP theorem. Mastering these concepts is foundational for anyone looking to design, build, or even just deeply understand the complex, scalable systems that power our modern digital world. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.